Welcome to the Deep Dive. Our mission today is to travel back, way back to the mid-1960s.
And we're going to trace the really winding, sometimes baffling path that led us to our current standard model of the universe.
Right, the Lambda CDM model. And we're using the personal history of Nobel laureate P. James E. Peebles as our main guide here.
It's a great way to see how this monumental theory was built on, well, shockingly little evidence at the start.
So what was the starting point, like in 1964?
Well, the basic idea was there, a homogeneous, expanding universe governed by general relativity. But the key thing, and the sources really stress this, is that it had scant observational support.
So it's just this beautiful theory kind of floating there, waiting for some proof.
Exactly, a framework waiting for validation, or, to completely collapse.
And that validation, or the search for it, really kicked off with the idea of a hot Big Bang.
Yeah, that was Robert Dicke, Peebles' mentor at Princeton. He had this hypothesis that if the universe expanded from some super hot, dense state, it must have left behind a fossil.
A kind of echo.
An echo, yeah. It's a detectable radiation, the cosmic microwave background, or CMB. So he told his team role, Wilkinson, Peebles, go find it.
And this is where the story just gets wild. Because while they are actively looking for it, building the equipment...
It had already been found, years earlier.
At Bell Labs. And they just thought it was noise.
He called it unexplained excess noise. It was like a dirty little secret in their experiments. They just baked a 2 Kelvin environmental noise factor into their equations to account for it.
A persistent fudge factor.
It wasn't until Arno Penzias and Robert Wilson decided to finally track down the source of this irritating hiss, which, by the way, they first blamed on pigeon droppings in their antenna that they heard about the Princeton group. And suddenly it all clicks. Their noise was the fossil of the hot early universe.
That story is a perfect illustration of what the sociologist Robert Merton called multiples. These ideas that are just kind of in the air.
And it happened over and over. Peebles and Jakob Zeldovich, on opposite sides of the Cold War, independently came up with the exact same solution to a problem in Big Bang models.
And it wasn't just them. Even the theory of how elements were formed was being worked on at the same time by groups in the US, the USSR, and the UK.
But once the hot Big Bang was really confirmed, around 1990 with the COBE experiments, it immediately created a huge new tension.
Okay, let's unpack this. The smoothness conflict.
Yeah, so the CMB spectrum was found to be wonderfully close to thermal. The hot Big Bang was, a lock.
But if the early universe was this hot plasma, all the normal matter, the stuff that makes us and galaxies, was coupled to light.
Right. So as gravity started to pull that matter into clumps, it should have left massive disturbances, huge smudges all over that CMB map.
But it didn't. The CMB was observed to be incredibly smooth. Far, far smoother than the clumpy mess of galaxies we see today.
So the question becomes, if all matter was baryonic, how did any structure form at all without messing up the CMB? It shouldn't exist.
So fix
the only way out, which again, Peebles and Zeldovich's groups figured out independently, is that baryonic matter must be just a trace element.
A tiny fraction of the total.
Exactly. Most of the matter in the universe has to be dark. It doesn't interact with light, so it can start clumping under gravity without disturbing that pristine CMB.
But there was a key difference in their ideas, right? This wasn't a perfect multiple.
Right. And this is Peebles' singleton contribution. Zeldovich's group initially favored hot dark matter, probably fast-moving neutrinos.
What's the problem with it being hot?
Well, hot particles move too fast. They would essentially smooth out any small initial density fluctuations. They would erase the very seeds you need to grow galaxies.
So Peebles' crucial insight was that it had to be cold dark matter, CDM. Something slow-moving with low pressure, so those little clumps could survive and eventually merge.
That gave us the scaffolding for the universe. But we were still missing the final piece of the puzzle, the lambda.
From the redshift data in the 80s.
Yeah, Davis and Peebles mainly. Their surveys suggested the mean mass density of the universe was just too low.
Which means that even with all that cold dark matter, there wasn't enough gravity to slow down the expansion. The universe was expanding faster than escape velocity.
The model didn't fit. So in 1984, Peebles sort of dusted off Einstein's old cosmological constant lambda as a way to accommodate this low density.
An accommodation that became the single biggest component of the universe. Dark energy.
And that, right there, is the Lambda CDM theory. It's now supported by this deep web of evidence. The redshift magnitude relation, the CMB anisotropy, mass density measurements.
It's just an incredible structure built from a foundation that started with, as you said, scant observational support.
It is. We can be pretty confident that any future better theory will have to look a lot like Lambda CDM. But, and this is really the final thought for you to chew on, while the model is a huge success, we only actually understand the physics of about 5% of it.
The normal matter.
Right. The other 95% is dark matter and dark energy, and we still have no fundamental idea what dark energy, what lambda actually is. The model works beautifully, but it's also telling us we're still profoundly in the dark.